Astronomers once believed the boundaries of heat in the cosmos were dictated by stars. Nuclear furnaces, blazing with the power of fusion, were thought to be the natural ceiling of temperature. Yet observations in recent years have revealed something unsettling. A planet so extreme, its surface burns hotter than the very stars against which we once measured cosmic fire. This is not the gentle warmth of a sunlit Earth, nor even the smoldering furnace of Venus. It is a crucible of heat that defies the categories we use to order the universe. This world is known as Kelt 9b, a gas giant circling a massive blue-white star some 650 light-years away in the constellation Cygnus. From a distance, its orbit may look ordinary, but closer inspection reveals a nightmare of physics. With surface temperatures rising above 4,300 degrees Celsius, it eclipses the very red dwarfs that form the majority of stars in our galaxy. In human terms, it is hotter than molten iron, hotter than steel forges, hotter even than many stellar cores at the threshold of fusion. A planet that burns like a star, yet is trapped in the identity of a world. The human mind struggles to conceptualize such extremes, but psychology has long shown how perception bends under impossible scales. When faced with magnitudes that defy bodily reference, heat greater than fire, distances vaster than thought, the brain slips into abstraction. Cognitive scientists call this magnitude neglect, the tendency to flatten incomprehensible numbers into symbolic impressions. Much as a child cannot distinguish the felt difference between a million and a billion, the mind cannot truly grasp temperatures thousands of times beyond survival. To think of Kelt 9b is to press against the limits of cognition itself, where understanding turns to illusion. This disorientation is not unique to astronomy. Throughout history, human cultures confronted the infinite with ritual and myth. Ancient Vedic texts describe the sun as a furnace of divine punishment, its flames consuming the unworthy. Norse mythology spoke of Muspelheim, a realm of fire so consuming that even gods feared its boundary. In these traditions, fire beyond human comprehension was not merely a natural force, but a psychological abyss, a heat that undid perception and destabilized meaning. The discovery of a planet like Kelt 9b revives these symbolic anxieties, translating ancient myth into astrophysical fact. Modern neuroscience offers a parallel lens. When exposed to overwhelming sensory input, light too bright, heat too intense, sound too loud, the brain's thalamic filters fail to regulate the flood. Instead of measured processing, consciousness becomes saturated, dissolving into disorientation. In laboratory settings, researchers such as Donald Hebb in the 1950s observed how sensory overload blurred cognition, producing hallucinations and altered states. To imagine standing at the threshold of Kelt 9b is to imagine perpetual overload, a storm of photons and heat sufficient to unravel neural coherence. It is, in effect, an astronomical hallucination. The planet therefore becomes more than a physical discovery. It is a case study in how science destabilizes certainty, how what we once believed fixed is revealed as fragile. Planets, in the human imagination, were cooler companions to stars, shadows to their brilliance. Yet here stands a world that inverts the hierarchy. If stars define heat and a planet surpasses stars, then the categories themselves collapse. Such collapse mirrors psychological disruption, the moment when the frame of reference breaks and the mind scrambles for stability in the absence of familiar boundaries. Kelt 9b is not simply hot, it is cognitively destabilizing. It erases the line between what is supposed to be and what is possible. And just as exposure to overwhelming sensory input forces the brain into altered states, So too does this discovery force thought itself into a new configuration. The illusion of order gives way to the raw violence of extremes, and the mind, unable to rest in certainty, is compelled to wander deeper into the abyss of what heat and matter can truly become. Heat in the cosmos originates from the most elementary transactions of matter, where nuclei collide, fuse, and release energy in bursts that ripple through space. Stars are the principal stage for this process. They are vast furnaces in which gravity and quantum mechanics conspire, forcing hydrogen atoms into contact at pressures and densities unimaginable on Earth. The result is nuclear fusion, a reaction that turns mass into energy, transforming stars into engines that can shine for billions of years. At the heart of a typical star lies a plasma of protons, electrons, and helium nuclei, a roiling medium in which temperature is not merely a measure of heat, but a reflection of the average kinetic energy of countless particles. In a plasma, electrons are stripped from atoms, and the resulting soup of charged particles conducts energy with extraordinary efficiency. It is this plasma that sustains the radiance of stars. Temperatures in stellar cores often exceed 15 million degrees Celsius, a level required to overcome the Coulomb barrier, the natural repulsion between positively charged protons. What emerges from this process is not an ordinary flame, but a continuum of radiation across the electromagnetic spectrum. Photons produced in the core can take tens of thousands of years to migrate outward, colliding with particles in dense layers of stellar matter before finally escaping into space. By the time they reach the stellar surface, they carry with them the signature of the star's temperature, which astronomers measure through spectroscopy. The color of a star is no simple aesthetic quality, but a record of atomic transitions and thermal states. Stars are classified along the Morgan-Keenan spectral system, from cool red M-type dwarfs with surface temperatures near 2,000 degrees to blue-white O-type giants exceeding 30,000 degrees C. Our Sun, a G-type main-sequence star, lies near the middle of this scale, with a surface temperature of roughly 5,500 degrees C. The classification is not arbitrary, but tied to the physics of stellar atmospheres. Cooler stars allow complex molecules to form, while hotter stars strip atoms of electrons, leaving behind spectra dominated by ionized metals. The light we see from any star is a chemical fingerprint burned into radiation. Yet stars are not static flames. They live and change according to their mass. The smallest red dwarfs fuse hydrogen so slowly that they may burn for trillions of years, outlasting every other kind of star. By contrast, the most massive O-type stars consume their fuel with ferocity, collapsing and detonating in violent supernovae after only a few million years. Heat, in this sense, dictates destiny. The hotter the star, the shorter its existence, and the more violent its transformation. To study stellar heat is to trace the life cycle of the cosmos itself. Astronomical heat has always stretched human imagination. Early Greek philosophers proposed that stars were fiery stones, sparks embedded in a crystalline sphere. In medieval Europe, stars were sometimes considered pure manifestations of the element fire, shining incorruptibly against the backdrop of the heavens. The scientific revolution overturned these images, but the language of fire and furnace remains embedded in modern descriptions. Even in physics textbooks, stars are routinely likened to burning spheres, though no combustion takes place in their interiors. It is a metaphor that hides as much as it reveals. Psychologists studying conceptual metaphors have noted how deeply such analogies shape our understanding. George Lakoff and Mark Johnson, in their work on embodied cognition, argued that abstract thought is scaffolded by bodily experience. To speak of stellar heat as fire is not simply poetic, it is a cognitive strategy that grounds incomprehensible magnitudes in the sensory world of touch and vision. But such strategies are vulnerable to distortion. They make stars seem knowable when, in fact, the mechanisms that sustain them are alien to ordinary human experience. A star is not a flame, but a plasma driven by equations of quantum tunneling and gravitational equilibrium. The Sun itself has provided psychologists with material for studying perception under extremes. Prolonged exposure to direct sunlight without shade, especially in desert environments, can provoke disorientation, hallucinations, and states of trance. Accounts from explorers such as Richard Burton during 19th-century expeditions in Arabia describe visual distortions and altered consciousness induced not only by heat, but by the glare of the sun across endless sand. Modern neuroscience attributes these states to disruptions in the hypothalamus, which regulates body temperature, and to overstimulation of retinal photoreceptors, which can provoke phosphenes and visual noise. The mind falters under the weight of heat, translating physiology into illusion. When scientists measure the surface temperatures of stars, they are not peering into a fire, but into the limits of perception. Instruments expand our senses, converting wavelengths invisible to the eye into graphs and spectra. Yet the human brain interprets those graphs with the same neural machinery that once stared at campfires or hearth flames. There is a mismatch between scale and intuition, between what data presents and what cognition can comfortably accommodate. This mismatch is the ground where illusion germinates. We imagine what stars must feel like, though no direct experience can validate the imagination. The heat of stars also becomes a cultural axis. Civilizations aligned calendars, myths, and religious rites with solar and stellar cycles. Ancient Egyptians marked the heliacal rising of Sirius, associating its brilliance with the flooding of the Nile. The Zoroastrians regarded fire as the purest element, linking terrestrial flame to the stellar fire that governed cosmic order. In each case, stellar heat became more than physics. It was order, fate, and divine presence. The psychological impact of associating heat with power shaped not only cosmology, but political authority. Kings and emperors compared themselves to suns, their rule legitimized by metaphorical radiance. In modern laboratories, heat continues to act as both physical and psychological limit. Experiments on thermal stress have shown that exposure to extreme heat reduces cognitive performance, slows reaction times, and increases irritability. At around 40 degrees Celsius, the brain begins to experience measurable declines in working memory and executive function. Theories of cognitive load explain this as a redistribution of metabolic resources. The body prioritizes thermoregulation, leaving fewer reserves for abstract reasoning. If such impairment occurs at ordinary terrestrial extremes, what cognitive framework can truly accommodate temperatures of thousands of degrees? The very act of contemplating stellar heat pulls human thought into states where categories blur. Physics becomes entangled with psychology, astronomy with myth, and science with illusion. To understand how stars achieve their heat is to trace the balance of forces that sustain the cosmos, but also to expose the fragility of human perception in the face of extremes. And as inquiry moves from the heat of stars to the heat of stranger worlds, the foundations laid here bend toward questions that press even harder against the boundaries of comprehension.
The path to identifying a planet hotter than stars began not with myth or metaphor, but with instruments designed for precision far beyond human vision. Astronomers searching for exoplanets have relied heavily on the transit method, a technique in which a planet's passage across its star produces a measurable dip in brightness. Even the faintest drop in starlight, often less than a fraction of 1%, can reveal the presence of a massive body. It was through such subtle fluctuations that the planet known as kelt 9b was first registered in 2016 by the Kilo Degree Extremely Little Telescope (KELT) survey. The survey itself was an anomaly in modern astrophysics. While many observatories depend on enormous, multi-million-dollar instruments, the KELT project deployed modest-sized telescopes with wide fields of view, designed to scan large portions of the sky for stellar brightness variations. Coordinated across observatories in the northern and southern hemispheres, KELT prioritized scale over grandeur. It was in these wide sweeps of starlight that the peculiar signals of KEL 9, an A-type star, emerged, and the extraordinary characteristics of its planetary companion began to surface. The host star, catalogued as HD 195689, revealed through photometric data a consistent pattern, dips in brightness recurring every 1.5 days. The regularity indicated a planet in a tight orbital embrace, closer to its star than Mercury is to the Sun, yet with a mass nearly 3 times that of Jupiter. Early measurements stunned the observing teams. Gas giants of such size were expected to orbit far from their parent stars, in stable, cool regions where hydrogen and helium could condense. To find a planet of Jupiter's scale pressed so close against the radiation of a stellar furnace contradicted expectations shaped by decades of solar system study. The validation of the signal required more than photometry. Astronomers turned to the radial velocity method, measuring the slight wobble of the star induced by the gravitational pull of its companion. By tracking the Doppler shifts in spectral lines, they could confirm that the dimming was not the artifact of a binary star but the transit of a planet. The results held firm. The stellar motion matched the predicted influence of a gas giant nearly 3 times Jupiter's mass. What was first a fluctuation in light became, through verification, a distinct planetary body. KEL 9b's presence challenged not only expectations of orbit, but also the chemistry of planetary existence. At such close proximity to its host star, equilibrium temperatures were predicted to reach levels incompatible with molecular stability. Calculations suggested that even the strongest chemical bonds would fail, leaving an atmosphere not of water vapor or methane, as with many gas giants, but of atomic fragments stripped bare by heat. Where other exoplanets promised exotic weather, this one suggested a cauldron of dissociation, an environment so hot that molecules could scarcely survive. The discovery immediately raised theoretical questions. Could such a planet endure, or was it in the process of disintegration? Models of atmospheric escape, derived from earlier studies of hot Jupiters such as HD 209458b, suggested that extreme ultraviolet radiation could strip vast amounts of gas into space. Observations of KEL 9b pointed toward even greater instability. The planet orbited so close that its upper atmosphere was expected to swell outward, nearly brushing against the gravitational boundary where material can be drawn directly into its star. In effect, the planet appeared to be boiling away into the void. Psychologically, discoveries of this kind occupy a peculiar space. The human mind is conditioned to expect patterns of familiarity. Planets cool, stars hot, matter stable within defined boundaries. When confronted with a world that collapses these categories, cognitive systems struggle to assimilate the anomaly. Researchers in cognitive dissonance theory, first formulated by Leon Festinger in the 1950s, describe how individuals respond when reality defies prior belief. One strategy is reinterpretation, bending facts to preserve mental equilibrium. Another is expansion, revising the framework to absorb the new truth. In the case of KEL 9b, the astronomical community had no choice but to expand, altering the taxonomy of planetary science itself. The sense of dissonance extended beyond professional astronomy. Public reaction to the announcement of a planet hotter than stars carried tones of disbelief and fascination. Media outlets presented it as a paradox, a world impossible by ordinary understanding. The paradoxical nature of such information activates what psychologists term the orienting response, a reflex first described by Ivan Pavlov, in which the nervous system locks attention onto stimuli that are novel, intense, or incongruent with expectation. A planet that is hotter than a star is precisely the kind of stimulus that rivets both lay audiences and scientific experts. The technical rigor behind the discovery, however, leaves no ambiguity. Spectroscopic data continue to refine measurements of its orbit, size, and atmospheric properties. The heat inferred from its star's radiation and from transit spectroscopy is consistent across independent studies. What began as a faint dimming of starlight has developed into one of the most extraordinary profiles in planetary science. A gas giant not merely hot, but seared into a state of near-stellar incandescence. The implications stretch far beyond cataloguing another exoplanet. Each layer of measurement exposes tensions in existing models of planetary formation and survival. Astronomers accustomed to classifying bodies by distance, mass, or thermal regime now confront a case that disrupts those categories, pulling attention toward the extremes of what matter and gravity can sustain. This disruption is not an isolated puzzle but a widening fissure, opening pathways into questions of how nature tolerates instability, how heat reshapes identity, and how categories dissolve when pressed to their breaking point. It is within that fissure that inquiry deepens, for the discovery is not static data, but an unfolding confrontation with boundaries that were once assumed secure. The signals from kelt 9b continue to accumulate, and with each refinement the world appears stranger, more volatile, and more precariously balanced between survival and dissolution. The search for planets began as a mirror to our own solar system, but in the widening field of discovery, mirrors distort, categories blur, and extremes assert themselves with an intensity that resists assimilation. When astronomers measured the thermal environment of kelt 9b, they were confronted with numbers that blurred the conventional boundary between planetary and stellar conditions. The dayside temperature was estimated to reach around 4,300 degrees Celsius, a figure that exceeds the surface heat of many red dwarf stars, which often glow at 3,000 degrees Celsius or less. This inversion, the idea that a planet could surpass the thermal radiance of stars, was not an exaggeration but a direct calculation grounded in spectroscopy and orbital mechanics. Spectroscopic analysis revealed that the atmosphere on the planet's illuminated hemisphere does not behave like that of a gas giant in the solar system. Instead of molecules circulating in complex weather systems, the extreme heat tears bonds apart, leaving individual atoms drifting in a haze of incandescence. Hydrogen, iron, titanium, and magnesium exist in vapor form, detectable not as chemical compounds but as spectral lines of isolated elements. In this way, kelt 9b resembles a star's photosphere, a radiant layer of plasma where atomic transitions dominate. To call it a planet stretches the word into unfamiliar territory, for its very air resembles the surface layers of stellar bodies. The intensity of this heat is not a passive measurement. Temperatures of thousands of degrees create a radiative feedback that reshapes the planet's appearance. Astronomers have noted that kelt 9b glows in its own right, emitting visible and infrared light not merely by reflecting its star's radiance but by thermal emission. The planet becomes, in effect, a secondary beacon, a mirror that does not only bounce back starlight but generates its own luminosity from within its heated atmosphere. In the darkness of space, it burns with a stellar quality that further destabilizes its identity as a planet. The comparison with stars is not merely poetic. Red dwarfs, which constitute the majority of stars in the Milky Way, often radiate at surface temperatures between 2,500 and 3,500 degrees Celsius. kelt 9b's measured heat eclipses those values, which means that an observer measuring radiation without context could mistake the planet for a faint stellar object. This inversion unsettles the taxonomies of astrophysics. Where once temperature was a reliable discriminator between stars and planets, the discovery of this world dismantles that neat division. Heat is no longer the property that separates stellar from planetary, but a spectrum across which both categories can overlap. From a psychological perspective, the confrontation with such overlap reflects a deeper human unease with blurred categories. Cognitive scientists such as Eleanor Roche demonstrated how the mind organizes the world into prototypes and boundaries. A bird flies, a fish swims, a star burns, and a planet reflects. When an entity crosses these categorical prototypes, when a bird cannot fly, or a fish walks, or a planet burns brighter than a star, the mind reacts with heightened attention, often bordering on discomfort. The fascination with kelt 9b is inseparable from this disruption of cognitive order. Its heat is not just physical intensity but categorical transgression. Historically, transgression of boundaries has often been narrated in myth through images of fire. The figure of Prometheus, who stole flame from the gods to give to humanity, embodied the danger of bringing divine heat into mortal domains. In Hindu cosmology, the fire deity Agni exists in liminal spaces, between earth and sky, between life and death, consuming offerings while sustaining cosmic order. The association of fire with threshold and danger resonates with the modern discovery of a planet that seems to sit uneasily between categories, glowing like a star yet bound like a world. The human imagination gravitates toward such thresholds, sensing both their promise and their threat. The planetary atmosphere's incandescence also introduces questions of perception. If one could hypothetically observe the surface of kelt 9b at close range, though no human physiology could withstand such proximity, the experience would exceed the limits of sensory processing. The eyes would encounter radiation levels capable of overwhelming photoreceptors, producing what neuroscientists call retinal bleaching, where visual cells are saturated to the point of dysfunction. The result would not be enhanced sight but blindness by brilliance. In this way, the planet is not only uninhabitable physically but perceptually. It cannot be seen as it is without destroying the act of seeing itself. Beyond the sensory threshold, the heat carries implications for time. At such elevated temperatures, chemical reactions occur at accelerated rates, molecules colliding and dissociating with extraordinary frequency. Psychologists studying the temporal binding effect have noted how the human brain compresses or expands time under conditions of heightened stimulus. To imagine existing, even briefly, in an environment where atomic activity races at these speeds is to imagine time itself distorted, compressed into a blur where ordinary intervals lose coherence. Though purely hypothetical for human experience, the concept illustrates how extremes of heat intersect not only with physics, but with cognitive models of duration. The very act of calculating these temperatures is an achievement of indirect measurement. No probe could survive approach, and no spectrograph can physically sample its atmosphere. Instead, astronomers rely on subtle shifts in light during transits, teasing out spectral fingerprints that reveal the presence of vaporized metals and hydrogen in a state of constant excitation. The precision required for such inference underscores the paradox that an environment more extreme than many stars can be detected and described from a vantage point hundreds of light-years away, while remaining forever beyond direct touch. The distance preserves observation but denies contact. Yet the heat is not uniform. The planet's tidal lock ensures that one hemisphere faces its star unceasingly, while the opposite hemisphere remains in perpetual night. This division produces a stark thermal contrast, where the day side glows at stellar intensity and the night side lingers in comparative darkness. The gradient between them is a battleground of forces: winds, jets, and turbulence racing at thousands of kilometers per hour as the atmosphere struggles to redistribute heat. The very air is in flight, attempting to balance an imbalance so great that stability remains uncertain. The image of a world glowing hotter than stars is already destabilizing, yet it is only a partial glimpse of what unfolds under such extremes. Beyond the brilliance of its surface lies the orbit that locks it into relentless exposure, the gravitational leash that ties it to a furnace it cannot escape, and the perpetual contest between heat and survival written into its very atmosphere. The measurements of temperature are not endpoints, but indicators of deeper processes that press against the very possibility of the planet's continued existence. The 9b's orbit is a study in proximity pushed to destructive extremes. The gas giant circles its host star at a distance of only 0.035 astronomical units, just 5 million kilometers, placing it nearly 30 times closer to its star than Earth is to the Sun. At such intimacy, gravitational forces exert an inexorable grip, drawing the planet into a state of tidal locking. One hemisphere perpetually confronts the radiance of the star, scorched without relief, while the opposite hemisphere remains in ceaseless darkness, shielded yet deprived of direct stellar energy. The boundary between these regions is a permanent frontier of turbulence. The orbital period is astonishingly brief. A complete revolution occurs in just 36 hours. A year on Kelt 9b passes in little more than the span of 2 Earth days. This rapid circuit is not the gentle rhythm of planetary motion, but a violent tethering, a cycle of unrelenting exposure to stellar energy. The planet is not moving through space so much as it is being held in place, gripped by the competing forces of gravity and inertia, trapped in an orbit that ensures maximum irradiation. Each passage is a repetition of the same ordeal: unending day, unending night, and a constant atmospheric struggle to bridge the difference. The dynamics of such an orbit carry profound consequences. Tidal locking enforces asymmetry, and asymmetry breeds instability. The day side receives radiation of extraordinary intensity, enough to strip molecules into atoms, while the night side, deprived of direct illumination, relies on atmospheric circulation to import heat. The winds required for this redistribution are not breezes in any terrestrial sense, but supersonic jets, predicted to exceed several kilometers per second. These torrents of air carry with them vaporized metals and hydrogen, dragging incandescence across the terminator line, where day and night confront one another. In fluid dynamics, systems driven by gradients of this magnitude are prone to turbulence of unpredictable complexity. On Earth, pressure differences between warm and cool regions produce storms, cyclones, and jet streams. On Kelt 9b, the scale of contrast magnifies these processes into something closer to chaos. Theoretical models suggest atmospheric waves capable of spanning the entire circumference of the planet, oscillating as shock fronts where the thermal imbalance cannot stabilize. In such a regime, the concept of weather becomes inadequate. What unfolds is a planetary-scale struggle between two incompatible states, each sustained by orbital constraint. The psychology of unending cycles provides a curious parallel. Human beings exposed to environments where night and day are artificially suppressed, such as polar regions during extended summer or winter, often experience circadian disruption. Research by Jürgen Askhoff and colleagues demonstrated that the absence of external cues destabilizes biological rhythms, leading to insomnia, mood disturbances, and altered perception of time. On Kelt 9b, the cycle is not absence but excess. One half drowned in constant brilliance, the other deprived of it completely. If any organism were to exist under such circumstances, its biological rhythms would be driven not by cycles of light, but by relentless constancy, a condition that neuroscientists associate with disorientation and hallucination. The orbit also magnifies the intensity of gravitational interaction. Being so close to its star, Kelt 9b is subjected to tidal forces that elongate its shape, stretching the planet into a subtle ellipsoid. Similar distortions are observed in Jupiter's moon Io, whose interior is heated by tidal flexing from Jupiter's gravity, producing extreme volcanic activity. In Kelt 9b's case, the heating is not geological but atmospheric, as tidal energy compounds the radiative energy pouring from the star. The planet becomes both a prisoner and a participant in a violent gravitational relationship, its very structure molded by the orbit that sustains its existence. From the perspective of orbital mechanics, such proximity is precarious. Theories of planetary migration suggest that hot Jupiters like Kelt 9b did not form in their current locations, but drifted inward from cooler regions of their systems. This inward spiral, driven by gravitational interactions with a protoplanetary disk or neighboring planets, delivers them into perilously close embrace with their stars. In some models, this migration ends in destruction, the planet consumed by stellar gravity or stripped into fragments. The presence of Kelt 9b suggests a world caught in the latter stages of such migration, already deep within the zone of danger, yet lingering in a suspended state of survival. The metaphor of entrapment resonates with psychological experiments on constraint. Studies of learned helplessness, pioneered by Martin Seligman, revealed that organisms repeatedly exposed to uncontrollable stressors often cease attempts at escape, even when opportunities for relief arise. The orbital mechanics of kelt 9b reflect a similar pattern, an endless cycle, inescapable, bound by forces too vast to resist. Though the planet cannot possess cognition, the image of perpetual orbit against a burning star evokes the condition of being locked into stress without reprieve, a mirror for human anxieties about inevitability and confinement. The rapidity of the orbit also invites consideration of time as experienced from within such a system. General relativity predicts that intense gravitational fields and high velocities alter the passage of time relative to distant observers. Clocks orbiting close to a massive star would tick differently from those at greater distances, their rhythm distorted by space-time curvature. For a world like kelt 9b, time itself becomes relative not only in theoretical equations but in physical reality. A planet can whirl through a year in 36 hours, yet from a distant vantage point, the perception of that orbit shifts again, revealing the pliability of what seems fixed. Each revolution is a renewal of strain. The locked face bakes, the dark hemisphere cools, and the dividing line becomes a corridor of violence where winds howl in ceaseless transit. The orbit is not a stable dance, but a grinding, repetitive motion that enforces imbalance and magnifies fragility. With every circuit, the system sustains itself against forces that erode it, inching closer to outcomes that remain unresolved, whether in the form of gradual evaporation, tidal disruption, or transformations yet more violent. The atmosphere of kelt 9b is not a protective shell but a battlefield, where radiation, gravity, and chemistry contend without pause. Unlike gas giants of the solar system, whose atmospheres are dominated by stable molecules such as methane, ammonia, and water vapor, the environment on this planet is stripped to its atomic essentials. At temperatures above 4,000 degrees Celsius, molecular bonds cannot endure. What emerges instead is a gaseous ocean of dissociated elements, iron and titanium among them, vaporized into states ordinarily reserved for stellar envelopes. Spectroscopic surveys conducted with ground-based instruments and the Hubble and Spitzer space telescopes have revealed absorption features characteristic of these atomic species. The signatures are striking in their clarity, narrow bands that betray the presence of neutral and ionized metals drifting through a seething sky. These detections confirm that the planet is not only hot enough to disassemble molecules, but also sufficiently extreme to sustain continuous ionization, a condition where electrons are ripped from atoms by relentless radiation. The atmosphere, in this sense, is less a meteorological system and more a plasma sheath, resembling the chromosphere of a star rather than the cloud belts of Jupiter. The physics of such an atmosphere is dominated by escape. Heated to stellar temperatures, the outer layers swell outward, inflating into a tenuous halo that extends thousands of kilometers beyond the nominal planetary radius. Ultraviolet light from the host star drives this inflation, energizing particles to velocities that approach or surpass the planet's escape velocity. As a result, material streams into space in a slow but persistent outflow, forming a comet-like tail detectable in ultraviolet wavelengths. The very air of kelt 9b is slipping away, atom by atom, bleeding into the void under the assault of radiation. Models of hydrodynamic escape predict that such mass loss can reach tens of thousands of tons per second. For a planet of several Jupiter masses, this erosion is not immediately catastrophic, yet it reshapes the future of the planet across astronomical timescales. The boundaries of atmosphere and space blur, and the notion of a clear planetary surface becomes meaningless. Instead, the atmosphere grades into interstellar medium, a process of dissolution that undermines the very identity of the planet as a coherent object. It is a body that cannot contain itself, held together by gravity yet continually shredded by energy. The circulation within this atmosphere compounds the instability. Supersonic winds transfer heat from the illuminated hemisphere into the darkness, dragging vaporized metals across the terminator line. In these currents, iron atoms migrate from zones of incandescence into comparative shadow, condensing briefly before being reheated and torn apart again. Such cycles resemble nothing terrestrial. Weather on Earth is cyclical and bounded, with clouds condensing and dispersing in repeatable rhythms. On kelt 9b, the atmosphere exists in permanent transition, where condensation, evaporation, and ionization occur simultaneously at planetary scale. The psychological implications of such instability are significant. Human cognition seeks continuity in natural systems, constructing narratives of balance and recurrence. Storms pass, seasons return, and climates settle into knowable patterns. When presented with phenomena that lack repetition or stable equilibrium, the mind experiences difficulty in framing them. Cognitive psychologists have described this as pattern violation, a disruption that heightens arousal and activates regions of the brain associated with error detection, such as the anterior cingulate cortex. To confront an atmosphere that never stabilizes, where order is impossible, is to confront a kind of environmental chaos that resists comprehension. The chemistry of the atmosphere deepens the anomaly. On cooler exoplanets, astronomers often detect molecules such as water, methane, or carbon monoxide, each carrying implications for climate and habitability. On kelt 9b, water molecules cannot survive the heat. Instead, the spectral signatures reveal atomic hydrogen and fragments of heavier elements, suggesting that even the building blocks of life are disassembled. From a chemical perspective, the planet represents a reversal of synthesis. Rather than forming complex molecules, its environment enforces decomposition, unraveling matter to its most basic constituents. This reversal has consequences for astrophysical theory. If planets can exist where chemistry itself is dismantled, then the definition of a planet must expand to include regimes where matter refuses stability. The boundary between planetary and stellar chemistry becomes porous, and categories once thought distinct collapse into gradients of energy. The planet becomes an experiment written into nature, a site where physics explores conditions usually confined to stars. From the standpoint of perception, the existence of such an atmosphere challenges the human reliance on metaphor. To imagine air as fire, clouds as flame, or winds as jets of plasma pushes language to its limits. Neuroscience teaches that the brain relies heavily on analogy, mapping unknown domains onto known experiences. Yet in the case of kelt 9b, analogies fail. There is no terrestrial equivalent for skies of vaporized iron or winds that carry atoms at supersonic velocity. Confronted with conditions beyond analogy, cognition falters, leaving the phenomenon suspended in abstraction. The spectacle of atmospheric escape also raises questions about endurance. As the planet sheds material into space, it illustrates a process of gradual unraveling. Unlike a sudden cataclysm, this loss is continuous, a constant attrition that wears down structure without immediate destruction. Psychologically, this mirrors forms of chronic stress, where the body erodes under sustained pressure rather than collapsing in a single event. Research in psychoneuroimmunology has documented how prolonged stress hormones suppress immune response, leading to slow but inexorable breakdown. In the planetary case, radiation acts as the stressor, stripping vitality in a process without reprieve. The measurements that reveal this atmosphere are indirect but precise. As the planet transits its star, starlight filters through the extended gaseous envelope, carrying with it the fingerprints of absorption by metals and hydrogen. By passing these fingerprints, astronomers reconstruct the composition and dynamics of an atmosphere they cannot see directly. The act is one of inference, a translation of light into environment, bridging hundreds of light-years with equations and detectors. The fragility of interpretation mirrors the fragility of the planet itself, both vulnerable to distortion and loss. As data accumulates, the portrait of the atmosphere grows sharper yet more disquieting. Each new detection confirms instability, escape, and dissolution. What emerges is not a system seeking balance, but one accelerating toward transformation, shaped by forces that erode identity rather than sustain it. The winds carry atoms into night, radiation tears them apart, and gravity strains to hold what energy seeks to disperse. With every orbit, the contest continues, unresolved, with consequences that extend beyond the planet into the very structure of the surrounding system. At the center of Kelt 9b's ordeal stands its host star, an object that dominates the system not only by mass but by the sheer violence of its radiation. Classified as a B9.5, A0-type star, Kelt 9 radiates at an effective temperature near 10,000 degrees Celsius, more than twice as hot as the Sun. Its luminosity pours across the electromagnetic spectrum, with an especially intense output in the ultraviolet, a domain of energy particularly destructive to molecular bonds. The tyranny of this star lies not only in its brightness, but in the quality of its light, which strips stability from any world caught too close. A-type stars are transitional bodies, hotter and more massive than the Sun, yet not as short-lived as the most massive O or B-type giants. Their high surface temperatures prevent the formation of stable outer convection zones, giving them atmospheres dominated by radiative processes. This radiative dominance translates into streams of photons with energy sufficient to ionize, disintegrate, and destabilize planetary atmospheres. For Kelt 9b, locked into orbit at a perilous distance, there is no reprieve from the deluge. Every second is a bombardment of particles and waves that would render terrestrial air or oceans into vapor within moments. The sheer mass of the star intensifies its gravitational dominance. Weighing nearly 3 solar masses, it bends the surrounding space with an authority that leaves its planet with no conceivable path of escape. The gravitational well is deep, the orbital leash short, and the conditions of residence dictated entirely by stellar command. Kelt 9b exists not as an independent entity, but as a subordinate, defined and reshaped by its parent. Unlike the Sun, whose radiation permits stability for distant worlds, Kelt 9 asserts a rule that corrodes its satellite. The star is both master and executioner, maintaining the planet in orbit while unraveling its structure. The psychology of dominance offers a parallel to this celestial relationship. Studies in social neuroscience, particularly those analyzing the impact of power asymmetries, demonstrate how systems of control create both dependence and harm. Subordinate agents, whether individuals or groups, endure elevated stress when locked into hierarchies where escape is impossible. Cortisol levels rise, immune responses weaken, and cognition narrows under the weight of subjugation. In the cosmic register, Kelt 9b embodies this same condition, tethered by gravity, stripped by radiation, surviving only as long as the dominant power allows. From a stellar evolutionary perspective, the host star itself inhabits a precarious phase. A-type stars exhaust their hydrogen fuel at accelerated rates compared with Sun-like stars, contracting and brightening as their cores undergo shifts in fusion processes. Kelt 9, still on the main sequence, burns ferociously, yet its lifespan is measured in hundreds of millions rather than billions of years. For the planet caught in its glare, this brevity offers no mercy. The intensity of radiation across such timescales is sufficient to erode its mass, possibly to destroy it outright, long before the star itself evolves into later stages. The tyranny is both present and prospective, immediate in its effects and inexorable in its trajectory. The ultraviolet flux that streams from Kelt 9 has measurable consequences for atmospheric physics. Photons in this range carry enough energy to ionize hydrogen and strip electrons from metals, generating an environment of continuous excitation. Astronomers detect these processes indirectly through broadened spectral lines, their shapes distorted by the motion and energy of particles in flight. Each line is a record of domination, evidence that the star's radiation is not merely illuminating its planet, but actively reshaping its composition. The data is not static but dynamic, revealing a world in flux under perpetual assault. The orientation of the system adds further complexity. The 9b's orbit is tilted relative to the star's equator, a misalignment that suggests a violent past of gravitational perturbation. Such obliquity exacerbates tidal stresses, forcing the planet into a configuration that maximizes its exposure to stellar heat. Unlike systems where alignment allows some measure of stability, this tilt ensures that the relationship between planet and star is not one of harmony but of conflict. The orbit slices across the stellar field in defiance of symmetry, amplifying the consequences of radiation and tidal strain. If one considers the star as an environment, the planet is immersed in conditions equivalent to sensory overload. In human terms, sensory overload occurs when the nervous system is bombarded with stimuli beyond its capacity to integrate. Research on attention and perception demonstrates that such conditions induce anxiety, disorientation, and collapse of cognitive function. The planet, though devoid of nerves, is caught in a physical analog. Every square meter of its dayside is subject to radiation so dense that no structure can integrate or resist it. What results is not adaptation but dissolution, a constant unmaking that mirrors the psychological breakdown observed under overstimulation. The tyranny of kelt 9 extends beyond heat and light. Stellar winds, streams of charged particles accelerated from its outer layers, add another dimension of assault. These winds, far stronger than those of the Sun, slam into the planet's atmosphere, compressing its magnetic field if one exists, or stripping particles directly if it does not. Observations hint at extended tails of escaping gas trailing behind the planet, evidence that stellar wind erosion compounds the radiative loss. In this sense, the star does not merely shine upon its companion, but hammers it with material force, shaping and diminishing it in real time. The scale of dominance becomes apparent when one considers proportions of energy. The flux received by kelt 9b is thousands of times greater than that received by Earth. The contrast is not simply quantitative but categorical. Energy at this scale transforms chemistry into plasma, stability into volatility, identity into uncertainty. Each second of exposure rewrites the conditions of the planet, ensuring that its existence is always provisional, balanced on thresholds that strain against collapse. The tyranny continues with every orbit, every photon, every particle carried outward from the star. The imbalance between host and companion widens as the processes of erosion persist. What appears to telescopes as a luminous system of star and planet is, at finer resolution, a dynamic of dominance and subjugation, energy and attrition, gravity and loss. With each measurement, the evidence grows that the relationship is not static but evolving, carrying implications that stretch beyond a single planet to the very principles of survival in extreme stellar environments. The existence of kelt 9b raises questions that strike at the threshold of planetary survival. A gas giant so close to a massive hot star should, by conventional expectation, already have disintegrated or been consumed. Yet the planet persists, not intact in the sense of stability, but enduring in a suspended state where physical laws stretch to accommodate conditions near their breaking points. This endurance is not passive but dynamic, a process of balance where gravity, radiation, and orbital mechanics interact in ways that prevent immediate collapse while ensuring continual erosion. The gravitational field of kelt 9b is both its anchor and its shield. With a mass estimated at nearly 3 times that of Jupiter, the planet exerts a formidable pull on its own atmosphere. This gravity slows the rate of escape, countering the tidal forces and radiative pressure that seek to strip it bare. Yet this same gravity elongates the planet, deforming it under the stresses of its orbit, creating vulnerabilities where atmospheric particles can be more easily torn away. The planet survives by virtue of mass, yet mass is also what makes its body a target for tidal strain, producing a paradox of strength and fragility. Astrophysicists have modeled this survival in terms of Roche lobe geometry, the region of space around a planet within which material is gravitationally bound to it rather than to its star. For kelt 9b, the Roche lobe is constricted, a narrow boundary constantly tested by atmospheric expansion. Hydrogen atoms heated into escape trajectories often cross this boundary, surrendering to the gravitational dominance of the star. The planet survives not because it resists escape, but because the escape is partial, continuous, and gradual. Instead of catastrophic rupture, there is attrition without endpoint, a slow unraveling that allows endurance within loss. This precarious survival has a psychological analogue in the human experience of thresholds. Neuroscience has documented how organisms operate at limits of endurance, maintaining life under conditions of hypoxia, dehydration, or thermal stress that seem incompatible with continued function. Research on allostasis, the process by which the body adjusts to persistent stressors, reveals how systems survive by shifting baselines rather than by maintaining homeostasis. In such states, survival is purchased at the cost of strain, and the longer the state persists, the deeper the body moves into instability. Kelt 9b, in its own physical way, exists in an allostatic state, enduring through adjustment but never achieving balance. At the chemical level, survival manifests in the persistence of atomic transitions themselves. Despite the relentless ionization, the atmosphere continues to absorb and emit, producing spectral signatures that astronomers can detect. This persistence demonstrates that matter, even when pushed beyond ordinary limits, does not cease to function. Instead, it reconfigures, moving into regimes of behavior more characteristic of stars than of planets. The identity of the planet becomes ambiguous, yet the processes within it endure, carrying forward a kind of survival by transformation rather than preservation. The dynamics of survival extend to energy transfer. The intense irradiation from the host star does not merely heat the atmosphere. It drives circulation patterns that distribute energy across the planet. These winds, though violent, delay thermal runaway by moving heat into the nightside hemisphere. The result is not equilibrium but redistribution, a process that slows catastrophic loss while producing turbulence on a planetary scale. The planet persists because energy is never allowed to stagnate. Motion substitutes for stability, a dynamic survival born of perpetual restlessness. Human cognition is often drawn to images of endurance under fire, and the metaphor resonates here with particular force. Studies in resilient psychology, especially in trauma research, suggest that survival under extreme conditions often depends not on resistance but on adaptation, on finding ways to continue in altered form. Individuals exposed to chronic adversity may emerge transformed, their identities reshaped, their capacities stretched. In the cosmic analogue, kelt 9b survives not by resisting its star but by yielding, reshaping itself into a body that can endure partial loss and continuous stress. It is survival through concession rather than defiance. The persistence of this planet also carries implications for the fate of systems. If a world can endure conditions hotter than many stars, then planetary physics must be reconsidered not as a domain bounded by stable categories, but as a spectrum of possibilities. Kelt 9b demonstrates that survival can occur in states previously thought uninhabitable for planets, extending the concept of what a planet is and how it persists. The very existence of such a body forces astrophysicists to expand theoretical models to account for regimes at the edge of physical plausibility. Yet survival at such extremes is never secure. Every measurement of atmospheric escape, every model of tidal deformation, and every observation of chemical dissociation understands that endurance is provisional. Each orbit subjects the planet to renewed stress, and each orbit contributes to loss. The survival we witness is temporary by definition, not because destruction has arrived, but because the forces at play guarantee continued attrition. The timescales may span millions of years, yet in astronomical terms, such durations are fleeting. The survival of kelt 9b is a state of suspension, a moment extended across epochs, awaiting outcomes that remain beyond current observation. The concept of thresholds is central here. Thresholds of temperature, thresholds of radiation, thresholds of gravity and mass. To exist at such thresholds is to exist at the margins of what is possible. In human psychology, thresholds of perception reveal how easily the mind can be overwhelmed when sensory input exceeds limits. Phenomena such as sensory gating illustrate how the brain filters stimuli to preserve coherence. When this fails, perception fragments into overload. The atmosphere of kelt 9b cannot gate the energy of its star. Every particle is exposed, every layer penetrated, every molecule torn apart. Its survival is the survival of a system continually exceeding thresholds without collapse, persisting in a state of exposure that would annihilate lesser bodies. As observations deepen, questions sharpen. How long can such survival endure under attrition? What transformations will the planet undergo as erosion progresses? And how do these extremes shape our understanding of planetary resilience across the galaxy? Each new piece of data suggests not closure but escalation, revealing a system suspended between persistence and dissolution, carrying consequences that extend far beyond its orbit. The survival of kelt 9b cannot be disentangled from the processes that are simultaneously unmaking it. The planet exists in a state of gradual dissolution, where its boundaries blur under the dual assaults of radiation and gravity. This dissolution does not occur as a singular event, but as a continuous process of transformation, in which the very identity of the planet shifts from one category of object to another. It is not merely being destroyed, it is being rewritten by physics into a form that challenges the distinctions between star, planet, and interstellar debris. The first axis of dissolution is atmospheric. Heated beyond molecular endurance, the planet's gases expand outward into a diffuse shroud detectable across ultraviolet and optical wavelengths. This outflow is not symmetrical. It is sculpted into a trailing stream, a cometary tail of hydrogen and metals drawn outward by stellar wind and gravitational pull. Instruments capture absorption lines not only during transit but also before and after, evidence that the planet carries with it an extended envelope too large to be contained within its gravitational domain. Dissolution is visible not as absence but as excess, an atmosphere too inflated to be bound, bleeding steadily into space. The second axis lies in structural transformation. Tidal interactions stretch the planet, pulling its mass into ellipsoidal distortion. The stresses of this elongation alter internal dynamics, possibly redistributing heat within layers deep below the visible atmosphere. While gas giants of the solar system maintain relatively spherical symmetry, kelt 9b is forced into an unstable geometry, its shape a compromise between self-gravity and external forces. This distortion is not static. Orbital precession and variations in stellar output alter the degree of strain, producing cycles of stress that ripple through the planetary body. Survival in this sense becomes inseparable from deformation, the planet existing only in states of continual reshaping. The third axis is chemical. Spectra reveal atoms of iron, magnesium, and titanium in vaporized states, dispersed through a sky without molecules. Yet the process is not limited to metals. Models suggest that carbon and nitrogen, ordinarily locked in molecular forms, are liberated into atomic or ionized states, carried by winds across hemispheres where they may recombine only transiently before being dissociated again. The chemistry of the planet becomes a chemistry of impermanence, where bonds form only to be broken. Transformation unfolds not toward complexity but toward simplicity, the reduction of matter into its elemental scaffolding. The psychological resonance of such dissolution lies in the tension between identity and change. Human cognition attaches stability to categories. A planet is expected to be spherical, to contain molecules, to endure across orbits. When those categories disintegrate, perception struggles. Cognitive science has described this in terms of category collapse, a state in which the boundaries that support recognition dissolve. Under such conditions, the brain responds with anxiety and heightened vigilance, as it can no longer rely on familiar distinctions. 9b embodies this collapse on a cosmic scale. It is no longer entirely a planet, nor a star, nor debris. It occupies a shifting territory where categories dissolve into flux. Yet transformation is not equivalent to disappearance. The material lost to the star's gravity does not vanish but enters new trajectories, feeding the stellar environment. Escaping gases may form a circumstellar cloud, detectable as additional absorption during stellar transits. These materials may alter the star's spectrum, injecting complexity into the very light used to study them. In this way, the planet becomes a contributor to its parent's environment, feeding the tyranny that oppresses it. Dissolution becomes a form of incorporation, where fragments of the planet are assimilated into the processes of the star. The timescales of transformation demand attention. Hydrodynamic escape operates continuously, its rate dictated by stellar flux and planetary mass. Calculations suggest losses on the order of 10 to the power of 10 kilograms per second, figures that, though staggering, still allow the planet to persist across millions of years. Yet timescale does not dilute significance. On human scales, this endurance appears eternal, but on cosmic scales it is ephemeral. The tension lies in this disparity, survival stretched across epochs but bracketed by inevitable loss. The planet's present form is temporary, already yielding to a future where its mass, composition, and shape will no longer resemble what they are now. Transformation also reshapes the observational challenge. Each measurement captures the planet not as a fixed entity, but as a moment within a continuum of change. The kelt 9b observed today is not identical to the kelt 9b of past centuries, nor will it be the same in centuries to come. Telescopes collect photons that encode not only the present but the trajectory of dissolution, signals of matter in flight, of atoms escaping, of winds redistributing what remains. To study such a planet is to study transition itself, not a static body but a process unfolding in real time across light years. The metaphor of erosion in psychology offers another parallel. Long-term studies of stress and trauma reveal how persistent pressures erode identity not through single events, but through accretion of small degradations. The self remains recognizable but altered, worn into shapes unanticipated by its beginnings. The erosion of kelt 9b follows a similar logic. The planet persists, yet it is not the planet that once was. Each orbit brings subtle reductions, each exposure reshapes its atmosphere, each particle lost redefines its future. The identity of the planet is not erased but rewritten, survival inseparable from transformation. As dissolution progresses, questions of threshold re-emerge. How much mass can be lost before the planet ceases to function as a gas giant? Will its core, if one exists, be exposed, producing an object more akin to a remnant than to a living planet? Could the continuous escape alter orbital dynamics, shifting its path around the star? These questions underscore that dissolution is not merely passive erosion but active transformation, carrying implications for the fate of the entire system. The observations available so far suggest persistence within flux, endurance within loss. Yet each measurement hints at trajectories not yet realized, transformations not yet visible. The processes underway cannot remain static. Radiation, gravity, and chemistry continue their work, and the identity of the planet will shift accordingly. What emerges is not an answer, but a deepening uncertainty, a recognition that dissolution itself may be a state of being rather than a path to absence. 9b occupies a frontier where planetary science collides with astrophysical extremes. The concept of a planet has traditionally implied solidity of definition, a body in orbit around a star, large enough for self-gravity to impose spherical form, yet insufficient in mass to ignite nuclear fusion. By that standard, kelt 9b qualifies. Yet the conditions it endures erode the usefulness of such definitions, pressing language and classification to their thresholds. It survives at a horizon where categories blur, its very existence straining the conceptual framework used to contain it. One dimension of this horizon lies in thermal physics. The dayside temperature surpasses 4,000 degrees Celsius, a level indistinguishable from the outer layers of cool stars. At this heat, the planet radiates not only infrared but visible light, glowing with its own brilliance like a minor star. This radiative intensity alters its observational character. Astronomers can study the planet directly, detecting its light apart from its host. It is not only illuminated but luminous, collapsing the boundary between reflection and emission. The horizon of extremes is marked by this paradox, where a planet burns like a star without achieving stellar ignition. Another dimension is dynamical. Tidal locking has fastened the same hemisphere toward the star, creating an eternal furnace on one side and a realm of comparative shadow on the other. Yet this binary is not stable. Winds driven by temperature gradients sweep across the terminator, transferring matter from day to night and back again. Supersonic flows blur distinctions between hemispheres, redistributing energy in chaotic patterns that resist equilibrium. The horizon here is not a boundary but a turbulence, a zone where opposites mingle without resolution. At the chemical level, the horizon is one of disassembly. Molecules cannot exist in the dayside atmosphere. They are torn apart into atoms and ions, forming a gas that resembles stellar plasma more than planetary air. Even water, the most resilient of molecular markers, cannot persist under such conditions. The chemistry is stripped down to primitives, yet these primitives are dynamic, flashing into transient compounds as winds carry them across thermal gradients before they are dissociated again. The atmosphere becomes a laboratory of instability, where transformation is perpetual, but synthesis cannot endure. This state of extremity resonates with boundaries in human cognition. Neuroscience describes liminal perception, moments when familiar structures dissolve and the brain struggles to impose coherence. In altered states induced by sensory overload, meditation, or psychoactive compounds, individuals report experiences that defy categorical description. Kelt 9b mirrors such liminality on a planetary scale. It is neither planet in the conventional sense nor star in any true capacity, but something in between, a liminal object that destabilizes categories. To describe it is to inhabit the discomfort of thresholds, where definitions no longer suffice. The horizon of extremes extends into observational method. Instruments designed to probe ordinary exoplanets strain under the signals of kelt 9b. Spectra exhibit broadened lines from metals, signatures usually absent in planetary studies. Light curves deviate from simple models, as extended atmospheres alter the transit shape. Even the albedo, the reflectivity of the planet, becomes a contested quantity, as the balance between absorption, emission, and scattering defies ordinary modeling. The object resists reduction to parameters, requiring instead a rethinking of how planetary data is interpreted. Theoretical frameworks stretch as well. Conventional planetary evolution models assume that gas giants cool and contract over time, shedding heat acquired during formation. For kelt 9b, constant stellar irradiation halts this contraction, inflating the planet into dimensions larger than equilibrium predicts. The planet becomes an exception that demands modification of theory. It reveals that planetary life cycles are not governed solely by intrinsic processes, but can be radically altered by external tyranny. At this horizon, the laws are not broken but bent, revealing capacities of matter and energy unimagined in more moderate environments. Psychological studies of edge states offer a metaphorical lens. Individuals placed under extremes of isolation, sensory deprivation, or stress do not merely fail, they adapt in unexpected ways. Research into extreme environments, from polar stations to spaceflight, shows that cognition and physiology undergo transformations that cannot be predicted from ordinary conditions. Survival at extremes is not an extension of the ordinary, but a reconfiguration. 9b embodies this principle. Its survival is not an extrapolation of planetary norms, but a reconstitution of planetary being under extraordinary duress. The horizon is also temporal. Every orbit subjects the planet to the same cycles of exposure and strain, yet each orbit alters it incrementally. The outflow of gas reduces mass, the deformation reshapes interior dynamics, the irradiation alters chemistry. Over millions of years, these increments accumulate into transformations that redefine the planet's structure. To observe it now is to witness a moment in a process that will continue, carrying the planet towards states we cannot yet measure. The horizon is not only spatial or categorical but temporal, a boundary stretched across time where permanence dissolves into flux. The implications extend beyond this single system. If one planet can exist under such conditions, others may as well. Astronomical surveys already reveal hot Jupiters near other stars, each displaying variations in temperature, atmosphere, and survival. 9b is extreme but not solitary. It is a representative of a class that broadens the spectrum of what planets can be. The horizon of extremes is therefore not a point but a domain, populated by worlds that strain against the limits of matter. Each discovery expands this domain, multiplying the questions that demand explanation. The horizon presses further into conceptual space. Categories of planet and star, atmosphere and plasma, survival and dissolution, lose their separateness at these extremes. In their place emerge gradients, continuities where once there were divisions. Science thrives on such disruptions, yet they unsettle cognition, which seeks clear boundaries. The study of kelt 9b forces not only astrophysics but psychology to confront the unease of blurred categories, to acknowledge that nature resists the neatness of human schemes. As new instruments prepare to probe the system with greater precision, expectations gather around what more may be uncovered. Each refinement of data promises either confirmation of current models or revelation of new contradictions. The planet itself continues to orbit, each revolution a performance of endurance under extremes, each passage an invitation to measure again. Yet beneath the measurements lies a deepening sense that what is observed is not a fixed object but a moving threshold, a body caught between survival and dissolution, between planet and star, between definition and ambiguity.